Hey everybody, this is Larry. This is me going over Q4 of the recent contest, Rank Transform of Matrix. Sadly, to be honest, I didn't solve this during the contest. I solved this about like 10 minutes afterwards with some motivation. You could watch me solve this live during the contest and also afterwards, after the explanation part. Hit the like button, hit the subscribe button, join me on Discord, let me know what you think, let me know your questions. I appreciate your questions because the more questions you have, the more I know to answer them next time. And also I'll answer it this time as well, of course. Anyway, so this one, for me, this one is very tricky. And I'm going to bring up Point Brush for a quick I'm going to, so basically I'm going to go over two cases, not two cases, but I'm going to go over a different problem first. Not a different problem, just like just like a easier version of the problem, say, right? So let's say I have a easier version of the problem where all the numbers are unique, right? Well, if all the numbers are unique, then we can, this becomes a lot easier. Let's say we have a matrix. Let's actually add a couple more boxes, and the numbers really don't matter per se because they're unique. But basically, you can kind of think of it this way, right? So we could look at each cell as a node, and for each node, we have a pointer that goes from, you can think about it as each node, and that if a number is smaller than the previous number or another number on the same row or column, then you have a node, you have an edge from that node, right? So for example, let me use a color that is not, that's a little bit stand out. So basically, for example, you have 1, you have 2, you have 3, you have 7, you have 6, right? Something like that. And also let's just fill out the rows a little bit, or the column for one of them, something like that. Right. So the idea behind here is that, okay, so you have a matrix that's filled out, so we just have to draw these edges. So for example, in this case, 2 is bigger than 1, so you draw an edge here. 3 is bigger than 2, and also 3 is bigger than 1. 7 is bigger than all these numbers. But you get the point here, right? And also 7 is bigger than this 1. 7 is also bigger than this 2. And 7 is bigger than this 5 and 4. Though this is, you could keep on drawing. I mean, you get the idea here, right? So the idea behind this is that now we create an edge where we have essentially a dependency graph. Because basically, the way that I was thinking about it is that in this case, now that we have this dependency graph, and it's kind of intuitive, which is that to say in English, to articulate it in English, which is that you always want to do the 1 before the 2 before the 3 before the 7, and so forth, right? In this case, in the same row and column. And if you think about it that way, well, then you could also think about it in another way, right? Which is that 2 depends on the 1 to finish first before it can go. 3 depends on the 1 before it could go, and 3 also depends on the 2 before it could go. 7 depends on the 3, the 2, and the 1, right? So that's kind of a dependency graph, and if this rings a bell to you, then good. And if not, that's okay. This is why we're here. This is why we practice. I mean, I didn't solve this problem during the contest, right? So I'm not trying to shade, but basically after that, then you've got to the problem becomes a little bit more familiar in that it is just topological sort, right? What is topological sort? So topological sort just allows you to kind of, for each node, we only process a node when there's no edges looking out at it, right? Going out, right? And what I mean by that is that if you look at this graph right now that I drew, so first, well, there's no, first we're going to draw the, let me change the color again. First we're going to do this 1, and we're just looking at rows for now. We'll generalize it a little bit. We'll solve it as 1 because, well, because 1 has no outgoing edges, right? This is very basic topological sort. I recommend you practice up on that if that's not understanding, because I don't want to spend too much time on the topological sort portion, because I'll just say that this is a prerequisite, right? But we do the 1, and then after that, if this goes by too fast, that may be why. But yeah, and then next we do the 2, because now after you removed you process 1, 2 is good, right? Because now 2 has no edges going out, because it only has an edge pointing to number 1, but that didn't count, right? So, and so forth. And now you could get the intuition that when you do a topological sort, so that's one part. And then the other part is, how do you label them, well, right? Well, when you label them when for a given cell, let's say 7, right? So now we you may notice that this 7 also has edges pointing downwards, as well as to the left and to the right. I didn't draw that one, but so it has a lot of edges going left, right, up, down, right? Because 7 is a big number. And so by the time it's done, you can just look at the maximum number on the row or the maximum number on the column, and then just make sure that this is the biggest number after those numbers. So that's how you process each node. I'm gonna go over my code real quick. So in the case where so basically for each row I just keep track of the max number, and then for each max number I keep track of the rank, and I update the rank afterwards. This code may look a little bit weird, so I'll explain it a little bit. Okay, so that is how you would solve it if there was no unique numbers, right? And that would be pretty straightforward. Well, it was still hard because it still took me about an hour of implementation, maybe a little bit less. It's just that I was having issues with typing. No, it took me probably like half an hour just to kind of get all of it right, because there are some optimizations that you have to do, even though this is the core concept. So this, for me, this was a really tricky implementation problem. Though it turned out that there was a thing that I didn't consider, which made it interesting. But it's implementation problem because so let's say we want to draw these edges, right? Looking at this same graph, we're looking at 7. 7 has a lot of edges, if you could tell. In fact, 7, the largest number in the graph, in this case 7, say, will have, if you have, given that n is 500 and rows is also 500, so each cell could have up to 500 plus 500 edges, right? It's not quite like that, but because not every number can be the biggest number. But if you do some like n choose 2 math, right, like n square math, that still adds up. And given that n is equal to 500, that's gonna be too slow, right? So basically, what you have to do instead in this case is, instead of all these edges, okay, well, it's not erasing all these edges for me. So let's just pretend all the edges are erased. Let's just at least clear up a little bit. Okay. So let's say we cleared up all these edges. Okay, let's just say there's no edges, and I'll use another color. We'll use green. Let's say there's no more edges, right? But one thing you can note is that if 7 7 depends on 1, 7 depends on 2, 7 depends on 3, right? Well, that's a lot of edges. But we also know that in this case, that we don't need, you think about taking a class, right? And that's how I always think about topological sort and dependency graphs. I think about taking classes in college or something like that. You have to take, let's say you have to take you have to take quantum mechanics, and quantum mechanics requires, well, physics 1, physics 2, physics 3, and physics 4 or something like that, right? Which makes sense because quantum mechanics is hard. But you know, like, but if you ever look at your course book, they wouldn't literally list all these courses, right? So and I think that in an intuitive way, you know where I'm going to go with this, which is that you can just, if in this case, knowing that 3 depends on 2 and 2 depends on 1, and because this is not an arbitrary dependency graph, this is a dependency graph on just numbers, right? So you know that on numbers, if A is bigger than B and B is bigger than C, then A is bigger than C, right? So this is the transitive property, and because there is transitive property on ordering of this, so what we can do is actually, instead of drawing all these edges, and there'll be n square edges, because then choose 2 edges, right, for each row, and that just becomes way too big. You can actually just look from 7, you point at 3, actually, technically speaking, 7 point at 6, 6 point at 3, 3 point at 2, 2 point at 1, right? So that's kind of how I would think about this. And then once you do that, it becomes like a linked list, essentially. And you have n edges per row, right? And because of that, that's just going to be also n squared in total, because there's only n per row and n columns, I guess, say. So it'll be n times 2n, so it'll be 2 times n squared number of edges instead. So that is an optimization that is needed for this problem as well. So there are other things that you have to do with it, but yeah. So let's say now that this is unique. This is unique, and this is how you would solve the problem, because now you have this dependency graph, and I took a long time implementing it, but yeah. Now that you have this thing, so you can do a topological sort on it, and if all the values are unique, that's pretty much all you have to do, and that's how my first code works. So I had a couple of wrong answers during the contest. Oops, not this one. So I did do this in the first one, but I actually end up not going this well, though. We'll go over why this is the case. But yeah, I keep track of out degree, in degree, and stuff like that. But the problem is actually, and I will draw another one because there's a good edge case here. But the problem is non-unique numbers, duplicate numbers. How do you handle them, right? So I did not handle this well. But oops, let's go with black for now. We don't have to draw that many cells, I don't think. But you know, let's say we have let's say we have 0 here, 0 here, you know, I don't know, it doesn't matter here. -1, 2, 3, doesn't really matter as much as well. So it doesn't, right? So let's say this is our very rough matrix, right? Because the algorithm will mostly still work with it will mostly still work with topological sort, but now the problem is it's not true, it turns out, right? So basically what happens is that, okay, let's just draw an edge for this node here, right? Or edges for this row and column for this thing. So 0 points at 2, as we said, 3 points at 2, 2 points at 0, 3 points at 2, 4 points at 3, 0 points at 2, or 2 points at 0, sorry. I keep on saying it backwards, and so forth, right? Oops. And then in this case, 0 points at 1, 4 points at 0, 5 points at 0, right? So in this case, unfortunately, the thing is, the circled 0. That's the tricky part. So the tricky part is that right now, there's no edges going out to 0, right? But the thing is that there's also another node that has no edges. So you have this one, the -1. And so so the thing is that now, let's say we process this -1 first, so then we give this a number. Let me use another color. let's say for this cell, we give it number 1. So then in this case, and in this, because this 0 also doesn't have any dependencies, we also populate this as number 1. But now we have a wrong answer. We have a contradiction. We have a wrong answer. Sadness. Why? Because next we process this number. I'm changing colors again. Okay, that's too close. Yeah, because next we process this number, because now this number has no more outgoing edges because -1 is processed. And then now we have a contradiction, or just wrong answer, where this will be a 2 because we look at the 0 to -1, and well, and 0 to -1 will, the next number is a 2. But as you can see, this 0 is also this 0 is a 1, right? So that means that we're having some issues with our dependency graph. That it makes it not correct, and I didn't know how to handle this during the contest, because it took me a while to think about it, because and this is a good lesson for myself, just to kind of think about how I did it. And the key thing to note is that, to be honest, I underestimated this part of the problem. I thought that the hard part of the problem is just the dependency graph, the topological sort, and stuff like that. But it turns out that this and I thought that uniqueness was just like an edge case that I could handle with some if statements that I could fix later. I don't have to worry about it. Let me just focus on getting the code right, getting the code correct. But it turns out that this is not, as you can see, because during the contest, you can put, you could, if you try to do something greedy, like you could be like, oh yeah, you just kind of maybe change this one, right? Like maybe next we just go back and fix this one, or maybe you draw an edge here. There are a couple of different ways, but they're all just greedy. They're all heuristics. They depend on something that, you just reverse the order or just have something in a little bit different way. That's going to give you the wrong answer, right? So I knew that unfortunately, after I implement way too much, that's when I was like, oh snap, that's not good. But yeah, so about this time, during the contest, I was having a couple of Hail Marys where, like, okay, can I always go from like the smallest number to the largest number? I wasn't able to prove it during the contest. I only proved by AC afterwards, but it turns out that you can, because when you process in order, in a number order, no matter what, all your prerequisites are done. Because that means that, for example, if you process the zeros together, well, -1 will always have a smaller number and so forth. But so that's kind of the short story. But the only thing that is tricky is, but the only thing that's tricky with that is that you cannot just combine all the numbers together, because, for example, if you have another number, let's see, let me change the color again. Let's say we have number 0 here, maybe. In this case, right, this answer is actually 1. Right, let's say there's no more zeros in this case. This is not a 0, this is not a 0, this is not 0. Right, then in this case, this answer would be 1. Or yeah, and from that you could see that this group of zeros is 2, and this group, or this 1 0 is 1, right? So that means that you cannot just naively combine them and then sorting or something like that. Though it turns out that you can close to it. So what happens is that what happens is kind of fun, actually, because let's get rid of these colors again and again. Oops, how did that happen? So let's say we get rid of these colors. Let's say that we get rid of these colors. 0, right? Let's say this is a 0 now, right? Well, okay, let's just say this is a 0. ignore the blue, right? So that means that now this also has to be a 2, or at best a 2. It could be even higher number, right? But it has to be at least a 2. So let's say this we set at 2, and then this we set at 2, right? So now we draw this connection this way with the 2 zeros, and you can maybe even draw it this way if this was a 0 again. So this may so this is the kind of the insight that I had about. Unfortunately, I had about 10 minutes left in the contest when I made this insight, and I wasn't able to implement it very quickly because usually I am actually able to do this very quickly, but not this time because it is a 2-dimensional thing. So what ended up happening was that I just had some silliness around it. And also there was just like a lot of things with, and again, we have to be careful of how we do the how we kind of merge the connected components together, right? And what I mean by that is that is actually not a non-trivial, or it's not hard to implement, but it's something that you have to be careful about, because if you do the merging of these components naively, it could be n squared in the number of components or number of elements inside the components, and then that may give you a time limit exceeded. So you have to kind of reduce that to at least, you have to reduce that to as little as possible, and that's basically what I did. And then now I think we have enough to go over the code. Now, I haven't explained how I solved this yet, but that's basically the problem that is broken down. These are the observations that you need to make to solve this problem, right? And unfortunately for me, it took a little bit too long. But so basically now this is union find, a 2-dimensional union find. So I had some issues with this because just that I was a little bit rusty, because I'm so used to writing union find that in a certain way that I think I just didn't take account the 2-dimensional aspect. And again, union find is also a prerequisite for this problem. I might do a separate video on union find at some point, but for now, let's just say that this becomes instead of a regular parent where your parent is just the index of your parent is the index of the node. We set it to be the x and the y of the node. So that means that you still look at the parent of the node, but now it has a 2-dimensional aspect. And that's basically what I did. I've implemented, and because it is a little bit new to me, it took me a little bit longer than I would have otherwise. Maybe I could have finished it otherwise, but so that's why it took me an extra, I finished it about 10 minutes after the contest with a little bit of cheating. I took a look because the contest ended, so I just wanted to see if that was on the right approach, and I was. So I would have gotten it eventually during a contest, but I spent too much time on the other solution. But yeah, so this is a 2D union find. I just keep track of the parent, which is an XY component coordinates, and then I have to do some really fancy stuff to do the merging that we talk about, because you have all these numbers that you want to say, okay, let's say we have 2 1s, are they in the same group? Well, and now we have a connectivity problem, which is the same as actually Q3, where, okay, if A is connected to B, B is connected to C, so forth, right? A is connected to C. So we want to modify that in a way such that, let's say you have an entire matrix of zeros, right? Well, if you look at every zero, if you do a naive n-square loop for every zero against each other, that's your worst case. It's going to end up n to the 4th, or rows times columns times rows times columns, because you look at each element and then you're just looking at literally each element and then each element, right? So that's going to be n to the 4th. That's going to be too slow. So that is actually why I end up taking a long time as well, because I had to be smarter about that one. And So the key thing to notice is that you only, one is that you don't have to check every zero. You only have to check the zeros that are in the same row or the same column, and that's good enough. So that's basically what I did. This is, I don't know why this used to be something else. That's why it's called a queue. But basically this is just a grouping by the number. So this is, yeah. So for example, if the entire matrix is 0, then this would just have the entire matrix in X and Y. And then now for each number, I look at the vector that is given the number, and I sort it by the X coordinate first, because if you sort it by X, then that means that only then adjacent nodes may only adjacent values would have the same X, right? This is, you may have to visualize it, but basically, for example, if you sort like 1 5 and 1 6, 3 5 or something like that, right? Well, only adjacent values will have the same X. So once you sort that, you're able to get that from n to the 4th to n squared log n. So that's basically what I did here. And once you do that, that is fast enough. And I do the same thing with the other dimension. I sort by the y coordinates so that I could check merging by the y coordinates, right? I even have some print statement that I left out here, and luckily it didn't time out for that reason. And now we use the union find to merge adjacent nodes. If they have the same X or the same Y, we do the same for column, so going up and down. And then now we have this thing where now I could have maybe done this another way, but basically for every node, now I group every node of the same value. So let's say let's say k is equal to 0. For every coordinate, we look at the parent and we just group them by the same parent, right? So what I mean is that, okay, let's say you have 3 different components. So A, B, and C is connected to 1. D, E, and F is connected to 2. Then now we have 2 connected components, and then we just wanted to put them in the list somewhere, and that's basically what I did. I put it in a default dictionary of a list so that I just keep track of all the parents and their children in the union find sense. Basically, given a set, get all the components and put them together, and then after that, I put it in events, because that's how I look at them. Because you can have multiple components and then just put them on events, and then you sort them, and then you process them in order, and that's pretty much it. This is a little bit weird, but that's pretty much the hard part, because now you know that and the reason why this works with, I call it events, but maybe it's not an event, is because this is the same logic as the topological sort or the dependency graph, which is that when you process a number and you process every number smaller than it, that means that there's no outgoing edges, right? By definition, because you're only drawing edges to smaller numbers, right? So you process all the numbers behind it. So that's how you can sort by the value, and it'll be okay. It's just that before we might have different components in the same section, right? So yeah. And then now this is a little bit tricky to read, because I solved this a little bit after the contest. But basically now we try to get the rank of an event. And basically the rank of the event is just that for each row, we keep track of 2 things. We keep track of what's the maximum number that we used, or the last number that we used, basically, right? And that's basically just, the last number that we used for that column or row, so that you can use it again. So that has to be rank plus 1, right? And also the last number that used at that number. I did that. So the reason is that, for example, maybe this is a visualization, but the reason I did that is that basically, if the entire row is, the last number is a 2, then you want to use a 3. You also kind of look at your columns as well, or your rows and columns, so that you get the smallest number that is the next number from those 2 numbers. So that's why I have 2 for loops, 2 if statements here, and I also go through every node of the component to do that, because like going back to the visualization that we had before, basically we look at so let's say we're processing zeros. Okay, this is as undo as I can get. If we're processing zeros together, we try to look at, for each cell, we just look at what the next possible number is, and then we take the maximum of all those numbers, right? It's kind of intuitive, it kind of makes sense, hopefully, but that's what I do here. And so so that's just keeping track, and if it's the same number, then we use the same number, though I think this logic is not necessary anymore. I think it was from before, because I think this was a hack around components. Maybe I could be lying on that one, but basically that's the idea. And then after that, after we get the maximum rank, for each cell, we just update that to the rank, and that's pretty much it. And then we also update the rows and the columns to the new rank, and also the last value that we use, so that we can get the highest one. Because basically the new rank is either, if the last number uses the same number, then we just take the same rank, at most the same rank. Actually, this is not true, so I think we could just remove this, actually, because this cannot be true. Otherwise, this would be wrong. So actually, it's just that this case is actually no longer ever true. So that's why. So you can actually do something like this, which is way cleaner. Right? Because basically these are the same numbers used, and that's pretty much it. And then we update it afterwards, so that next time we do it, it'll be +1 from that. So very hard problem. There are a lot of different observations to make, and for me, unfortunately, I like I said, and you can watch me during the contest afterwards. It's really long. Fast forward for it, but I thought that the unique case was an edge case, so I didn't really plan my coding and my implementation for it. And also I had to do it with the naive topological sort, where I didn't do this thing of the events on what we said. One of the observation is that when you process the numbers in order, in the value order, if you already did all the numbers more than it, then that number has to be the next number processed. So I didn't make that observation or proof until like a little bit later. So I end up writing a lot more code. This is still a lot of code. This is 60 lines of code, but it is, at least much easier. At least it's doable during an hour. It's just that I didn't make that observation until much later on, about the edge case. So it's kind of cool. That's why I like this problem. Let's go over complexity real quick. So union fine, that's for now. I mean, I do path compression, so let's pretend it's all 1 for now. You can make that optimization with by rank if you really find that to be an issue, so that would be an upsolving thing. But this is just union fine. So I dedupe all the values in the same thing. So this number will have at most n square number of different keys. Like with every cell in the matrix is different, and this will be n square. And then the other worst case is that they're all in the same one. So actually that is the worst case, which is that then this would take n square log n time. We kind of talked about that. So and in that case it will take over 1. So this, I'm a hand wavy a little bit, but basically it is in between n square and n square log n is the worst case, because each cell can only be sorted like ones or something like that, and otherwise each cell is only in one thing. So let's say this is n squared log n. It's a little bit hard to understand though. But yeah, and then we sort again, and then this is just straightforward. We look at each cell at most once. So this is O of n for this is row of O of n, and this is O of rows times columns times log of rows times columns, to be more precise. In terms of space, all we use is a matrix and a matrix for union find, but this is linear in terms of the size of the input, so basically linear space. This is a tricky problem to explain. This is a tricky problem to solve. So I wish I did this during the contest, but I didn't really understand how hard this problem was until later on. I think if I made one of those two observations earlier on, then it would have freed me enough time to do the later ones. So there are two observations. One is that non-unique numbers. So if you have duplicate numbers, you have to do this thing with connected components so that they all get handled at the same time. And the other observation is that in a way it's greedy in that instead of having an explicit topological sort graph of pointers pointing to previous, if we just sort it by the value, then it would have no out degree by the time we process it. That would have fixed implementation a lot, enough that if I made one of those two observations, then I should have been able to solve it. If I made them earlier, I made them but really late in the contest. Yeah, so watch me solve it during the contest. Let me know what you think, and I will see y'all next contest, hopefully better. That was dumb. That to solve two problems, bonus problems. I know how to do this, but tricky to get it right. Maybe. Do the same number have the same rank? Not always. It's topological sort. There's each node there's 1,000. That's too many though, right? That's 250 million. Is it though? There's a lot of bookkeeping. Wow, people are fast. Okay. It's going to n cube in the lowest case term. Got to be a little bit smaller. Okay. I don't even know anymore. This is gonna be a nightmare. Only 8 people solved it, so I think this is pretty hard. But it should be solvable, just hard. Looks right so far. What I want to do is okay. Let's, this is an X. Let's make sure this one's okay. Degree of the index. I think I'm doing this wrong. Right? Degree. All these edges that are coming in. I'm just handling the unique cases pretty poorly. Maybe not. we have to. This is not quite right. And this is right, and then now. We have this. Should be 1 2 1 2, maybe not. Zero one zero one. Huh. Oh no, I'll degree 0. Oops. Do I need a degree? This is the next key. That's just by coincidence that it works, to be honest. Because I didn't do another dimension. Okay. Like that. 40 minutes. I should be able to do this. This is not going to be fast, but hopefully it works. This one, I need to transpose this. Why am I doing this? Oops. No, this is confusing as hell, but it's right. Whoops. Well, mostly right. That's good. Well. That feels wrong. Why not say so? One has a phone. That seems right. Oh, whoops. This is what happens when you copy and paste. And also, when you silly. Okay. This is kind of good. Nope. Okay. Nope. Come on, come on. Well, that's not good. Why would this TLE though? Oh, whoops. Well, almost good. How are you gonna get to 4? Oh, this happens again. We never need to do the queue more than once. Okay, fine. Oops. That's not quite right. No, this is right. Oops. Okay. I don't even need that. Oh well, it's not right. Oh, we don't handle all the numbers together. That was what I was worried about, but Okay. So let's do, okay, so I fixed that, but there's a lot of unprocessed stuff. Makes sense. Oh, this 2 doesn't make sense. But I think maybe my bookkeeping is wrong. Who has duplicate numbers? Oof. It's actually surprising. Let's fix this one first. This one. Oh, so actually my assumption is wrong with all this code, and I think in this case, because we don't. No, that's not true. It's just that maybe my edge is wrong, because it should not relax 0, 0. this if statement is if. This if statement is if is how. What is the new thing? Oh, now it's fixed, but well, maybe not. That's what happens when you copy and paste. I didn't. This is so hard to kind of up and down. Alright. Please. This, I knew this was gonna be a tricky one there, but I mean, I look like I'm close, but why is that? I do something wrong. This should be a 2. Why is that a 1 for me? Try it out. I'm close, but not good enough. So we want 0, 1, or 1, 0. It's just 1. Why? That means that this is weird. Get rid of what the users. So I did put 1, 0 here. Why is that? Because this should have a pointer to -17. The previous is pretty bad. Is there a -1 in this? No, but still wrong, so okay. I could just point this out. I have 20 minutes to debug this. Oh, well, I should fix this as well. Well, let's see if that fixes it, because I was just being dumb with the -1. Nope. I mean, that's definitely a bug, but maybe I've got unlucky. But okay. First column. We made this. 20 minutes should be enough, but really taking my time. That's the first column. Oh, negative 37 is the smallest number, right? Whoops. I can't do negatives in my head. Okay. So it is the smallest number in the column and the row, so that's right. But we have to do the one. So why is this a 2? Well, I mean, it's definitely still wrong, but it's a 2 because the row because we have to I get why it's wrong, but I have to think about how to fix it. I don't know. Maybe my assumption is wrong about the thing. So we have to do a match on all of them. This is valid if on the column this number is 0 and on the row, but I don't know how to merge this in a good way. Maybe I can't fix it because no, 71 people got it, so I don't know. Maybe I'm doing this in a weird way. Wow, people got it really quickly, so I don't know. Maybe there's a more parliamentary algorithm. I think I'm mostly right if there's no duplicate elements, but I don't know how to handle it. Because of this case. This is for a given column, there's an out degree, but how do we do that transitive? Maybe it's just a dumb algorithm that I don't know about. Maybe it's just some weird sorting thing. With a lot of code. But maybe I don't have to keep on following everything just yet. That didn't work. Why is that all once? Oh, I don't update it because I need it. I just worried this would time out, but or just being right would be nice. Guess I'm sort defense. Is this right? I guess this is right. It'd be kind of sad if this was right. I had this in the beginning, but I thought it would be something trickier. But we'll see. Let's not count out X just yet. Okay. Okay. This is the same case as before, actually, but which is kind of sad. But I looked at the one that was wrong and it was wrong. So, but like it fixed the one that it was wrong before, but it's wrong in another way. So that's not great. Why is this wrong? Can you get threes that together in a weird way? That was a Hail Mary anyway. I feel like I guess I misunderstood something fundamental about this. So -50 to 1 to 3. That's 3. This has to be a 4. Right. But this is a 3 because we processed this in the wrong order. This is a 3 because we processed this first, so we don't see that this is a 4. Seven minutes left. I'm just trying anything, to be honest. So, which is kind of a good sign that I have energy, but sometimes I just get lazy. But yeah. Is this right? I don't remember. I fixed this issue, but it looks good enough to give it a try with 5 minutes left. Yeah, I mean, I didn't think this was going to be right, to be honest. Because it's just greedy, pretty much. I feel like my first answer is kind of right, but clearly there's some weird edges stuff that I need to handle. If there were no unique numbers, I guess this could be right. Or if there were unique numbers. But what is wrong about this? And there's this one case I couldn't prove, which is that yeah, if the same number can have different values, which is what I did not prove. Unless it's some like weird union find thing, which maybe is true, to be honest. But okay, fine. I think actually I could. I think I could do this with union find, but it's a little bit awkward now. If I had enough time, maybe I could have done it. Now that I think about it, but I'm going to observe this until whatever. But I don't know. What a disaster. Let's do a quick short code review first. And I gave away like a lot of time on this one because I misread it. Yeah, let's go. Wow, 10 minutes. I mean, I think this is basically what my thing is. My first solution. I don't know how to handle I don't know how they handled I don't know how they handled the same numbers and stuff. But well done. Well done, good people. Yeah, and union fine. I guess union fine was the way to do it. I mean, this is pretty tricky, to be honest. I mean, I had the right idea, but implementation was the hard part for this one as well. Maybe I'm missing something still. I mean, because this is just, but I mean, yeah. I don't know. Maybe I won't go this route. Even my alternate code is really long. Oh no, this is my original code. Okay, let's take a look at this one then. Can I fix this code to be right? I mean, I had the right algorithm-ish, but not quite. Another disaster. I was not feeling good today too. But I wasn't able to get this one. I don't know how to handle the union fine stuff. I mean, I do, but maybe I just have to finish this. Okay, let's finish how to handle this. I mean, I guess I got the right idea. Wow, this code is way shorter, but this is actually literally what I'm doing, but with this sorting thing. I mean, this is an implementation problem for me. But I should be able to do this. I was, I don't know that I understand that. Because right now, like my algorithm is right, but I am not coding it quite right. Why is this like really funky thing? So now I'm just doing code review and trying to learn and try to understand. mean, this is essentially what I was doing. Is this okay? I guess this is fast enough. I thought that this may not be fast enough. So. The union. I mean, okay. Assuming that this is right, so I have the union. Yes. We just have to look for okay. Okay. So I mean, okay. 500 cube is too slow, right? Okay, so then that means I have to do something smarter. Now I'm a little tired, to be honest, but okay, I think we would just do something like okay, now we split it up. So now we just do define of xy. Let's so we still want k, but we want t sub k now, so that we process it twice. Oops. 32. Maybe that's not how the syntax works. I guess that's This must be what? Oops. I'm gonna change that. Is that right? Nope, still wrong. That's unfortunate. But they should have the same thing. Let's print out the parent just to see if we oops, that's not the one. Okay, so this is still gonna be the wrong thing. So this is the pen. This is itself. This is white. What? That doesn't make any sense. Did I mess something up? Yeah, okay. That seems right, though I don't know where this gets 3 from. Oh, this isn't even. Why is this? Why doesn't that give an error? Alright. Is that right? So basically I need about another 20 minutes, maybe. See if this is too slow though. So the thing was that I try to do things one way in the beginning. This way it works. This is also similar, but in a little different. I think the problem. Yeah, I mean, excuse me, sorry about that. Okay. Yeah. Ugh. Hey everybody, yeah, thanks for watching the explanations. If you're here, definitely appreciate it. Hit the like button, hit the subscribe button, join me on Discord, and yeah, I didn't do that well this contest, but I did learn a bit from the Q4. I liked it, I digged it, dug it. So it is what it is. Anyway, I will see y'all next explanation. Bye bye.